So the FIFO presented in this project, as stated by all the facts that I have mentioned, the first in, first out are essentially memory buffers used to temporarily store data until another process is ready to read it. The first byte written into a FIFO will be a first one to appear on the output. Typically, FIFOs are used when you have two processes that operate in a different rate. The FIFO module has two settings that can be configured to adjust the width and the depth of the FIFO. That is, the data underscore width variable adjusts the size of the data in and the data out buses so that you can write different size of bytes if needed into the FIFO underscore depth. The variable adjusts how big the internal memory of the FIFO is. So in order to write data into the FIFO, first push the data onto the data in bus and then strobe the write enable input high for 1 clock cycle. This will write whatever is in the data in into the FIFO's internal memory. So writing in bulk, the write enable signal can be left high while changing the data on the data in bus each clock cycle. When the full flag goes high, the FIFO's memory is full and will not accept any more writes until the data is read using the read enable input. This process is illustrated in the VHDL architectural software model as I have presented in this video. Here I generate the FIFO pointers, first in, first out. So when reset is asserted, both read and write pointers are set to 0. The FIFO empty flag is asserted and the read pointer points to the valid data. When the write operation starts, after writing the first data, the FIFO empty flag is deasserted and the write pointer increments. The read pointer is still addressing the contents of the first FIFO, that is the memory word. Immediately drives that first valid word onto the FIFO data output port to be read by the receiver logic. Therefore, the FIFO is empty when the read and write pointers are both equal. This condition happens when both pointers are reset to 0 during a reset operation, or when the read pointer catches up with the write pointer having read the last word from the FIFO. So a FIFO is full when the pointers are equal, that is when the write pointer has wrapped around and caught up to read the pointer. The asynchronous FIFO, first in, first out memory devices, refers to a FIFO design where data values are written to the FIFO buffer from 1 clock domain and the data values are read from the same FIFO buffer from another clock domain, where the two clock domains are asynchronous to each other. Here in this project, as illustrated in this video, the FIFO partitioning with synchronized pointer comparisons is used for comparing and synchronizing the design working on two clocks, one for transmission and one for receiving, which uses gray counters for comparison of full and empty registers of RAM, which is the FIFO buffer for writing and reading the data values. Therefore, data words are placed into the FIFO buffer memory array by controlling signals in one clock domain, and the data words are removed from one port of the same FIFO buffer memory array by control signals from a second clock domain. As a result, FIFO needs to buffer the data that need to be stored during the write cycle until it has been read in the read clock domain. So the depth of the FIFO depends on the data to be stored. The main objective of this framework is to develop and design an ASIC design artificial intelligence flow using 90 nanometer Synopsys design compiler to generate the netlist of the physical design, and to use Synopsys ASIC compiler to perform the placement and optimization in conjunction and followed by clock tree synthesis, routing, and chip design. So first, synthesis is achieved in front end using Synopsys design compiler, and then the netlist is generated. Afterwards, the physical implementation of this design is done using Synopsys ASIC compiler. Power optimization using RTL level optimization and setting up power constraints is also a function of this development. The design compiler uses technology libraries, synthetic or designware libraries, and symbol libraries in order to implement synthesis and to display synthesis results graphically. During the synthesis process, the design compiler translates the HDL or VHDL description to components extracted from the generic technology GTEC library and designware library. The GTEC library consists of all the basic logic gates and flip-flops, and the designware library contains more complex cells, for instance, adders, comparators. So both the GTEC and designware libraries are technology independent. That is, they are not mapped to a specific technology library. So design compiler uses the symbol library to generate the design schematic. I describe the design in RTL, register transfer level, and capture the timing constraints of this design, and also the behavioral description of the design, and using the HDL, in my case the Verilog VHDL as a hardware description language. Then I emphasize some functionality in terms of functional simulation and verification. So the RTL is tested for functionality and correctness of the design, and simulation involves event and cycle-based simulation. This takes place while our assertion-based verification is used to verify functionality and correctness of the design. I also make major emphasis in synthesis. And at the synthesis level, which takes the RTL hardware description and the standard cell library as inputs, I take care of the constraints such as timing, area, testability, and power are all taken care of. And the design verification methodology is used so as to test the functional correctness of the gate level netlist. Therefore, testing functional correctness involves testing and optimized design against the golden design description. And of course, the layout. This phase involves the backend of the ASIC design flow, which is implemented using ASIC compiler by Synopsys to include floor planning, placement of cells, and chip area, placement of input-output pads on the chip area. The clock tree synthesis is also performed in order to minimize space and power consumed by the clock signal. Placement and route is carried out on this specific design. The interconnect delays and parasitic values are based on wire load models, which is resistance, capacitance, inductance. It is calculated for place and route netlist. Design rule violations are identified in this process and also corrected. And the timing analysis is carried out to find any timing violations. Now it's time for reading the design. So, reading the design, which is having the hierarchies to be done, that is top, bottom, or bottom up. In this case, what I have done, because I'm designing a FIFO element, the top bottom is what I have chosen. Due to the top bottom hierarchy strategy, all the sub-modules will be read first, and then the top level. And this is how it is done. First, we analyze and elaborate the design. So the source code is usually best read in with analyze, elaborate. Executing analyze command performs the following: reads the VHDL source file, checks it for errors without building generic logic for the design. It then creates the library objects in an HDL independent format, and then finally stores the intermediate files in a location. However, executing the elaborate command performs the following tasks. It translates the design into a technology-independent design, that is GTEC, from the intermediate files produced during the analysis. It also allows changing of the parameter values defined in the source code. It also allows VHDL architecture selection, and it also replaces the HDL arithmetic operators in the code with the signware components. And finally, it automatically executes the link command, which resolves all the design differences. The read file executes the file when reads several different formats, that is .vhd, .v, .ddc, .db files. It also performs the same operations as analyze and elaborate in a single state. And it creates the .mr and .st intermediate files for VHDL. However, it does not execute the link command automatically. Defining the design environment by specifying operating conditions, specifying wire load models and system interface characteristics. Operating conditions include temperature, voltage, and process variations. On the other hand, the wire load models estimate the effect of wire length on design performance. And the system interface characteristics include input drives, input and output loads, and fan-out loads. The environment model directly affects the design synthesis results. So in design compiler, the model is defined by a set of attributes and constraints that a design using specific DC_shell commands.
The functional specification of the design is done. The HDL coding and VHDL in Verilog RTL. The RTL behavioral or functional simulation of the VHDL code. The logic synthesis, followed by test, insertion, and ATPG. Then the post-synthesis or gate level simulation, and finally floor planning and place and route. The synthesis process was divided into two segments. The first segment employed a bottoms-up approach using design compiler in which all top-level blocks were synthesized using estimated constraints. Also, the layout process was completed. Here, the gate level netlist is converted to a complete physical geometric representation. The first step was to do floor planning, which is the process of placing the various blocks and the I/O pads across the chip area based on the design constraints. Then placement of physical elements within each block and integration of all analog blocks or the external intellectual property cores is performed. When all elements are placed, a global and detailed routing is running to connect all the elements together. Also, after this phase, a complete simulation was done to ensure the layout phase was properly completed. Finally, the file produced at the output of the layout is the GDS2 file, which is the file used by the foundry to fabricate the silicon. The layout should be done according to Silicon Foundry design rules.
Basic physical design methodology, the implementation for memory modules. The front-end mode consists of generating the SPICE models, which gives you the layout views and timing models. It also estimates power delay analytically. On the back-end mode, it generates the SPICE models with layout views and timing models to perform DRC and LVS. You can perform at each level of hierarchy or at the end of the hierarchy, and simulates power delay, and it can also be back annotated.
The control logic drives the FIFO flag. FIFO empty, that is flags. No data is present inside the FIFO RAM. In the FIFO full, no data can be written to the FIFO memory. And FIFO almost empty / full is also supported. So the FIFO almost empty flags is when the FIFO is used in order to buffer input data stream of a device where the input and output data throughput is the same, but the timing is different, such as in input as burst data, output as continuous data. The FIFO is used to buffer the minimum number of bursts data in order to guarantee continuous reading from the FIFO without interruption. So in this case, the FIFO read control logic block checks for almost empty flags going high and set FIFO read control signals to read continuously from FIFO. In the dual port RAM model segment of the FIFO, it writes counter to address the right side of the RAM. It reads the counter to address the right side of the RAM, and the control logic aiming to update the right counter at each write data into RAM, and the read counter every time a data is read or is read from RAM.
The FIFO VHDL model has several settings and are configured to adjust the width and depth of the FIFO. The data width variables adjusts the size of the data in and data out buses so that one can write different sizes of bytes if needed, and the FIFO depth variable adjusts how big the internal memory of the FIFO is. In order to write data into the FIFO, first in, first out, first push the data onto the data in bus and then strobe the write enable input high for 1 clock cycle. It will write whatever is on the data into the FIFO's internal memory. Writing in bulk, the write enable signal is left high while changing the data on the data in bus each clock cycle. When the full flag goes high, this means the FIFO's memory is full and will not accept any more writes until data is read using the read enable input. If data is written while the full flag is high, it will be ignored. In the standard FIFO first in first out, when you write the first byte into the FIFO, nothing takes place on the data out bus until the read enable signal is pushed high for at least the clock cycle.
Once the byte has been written to the FIFO, the empty flag will go low. To read the next byte from the FIFO, strobe the read enable signal high for 1 clock cycle, and the next byte of data will be available to read the next clock cycle. When the last byte of data is pushed onto the data out bus, the empty flag will go high.